Hello guys, let's start with the equilibrium today. Well, read the definition first. Okay, so when a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, strike the liquid surface, and are retained in the liquid phase. It gives a rise to constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equal the number returning to liquid from the vapor. We say that the system has reached an equilibrium state. The mixture of reactant and product is called equilibrium mixture. The stage where there is no change in concentration is called dynamical equilibrium. Equilibrium involving ions are called ionic equilibrium. You can see the picture. Here is the picture. Let's talk about the equilibrium in a physical process. The most famous example of physical equilibrium is the phase transformation process that is given below. The first is solid to liquid, next is liquid to gas, then solid to gas, right? These are the phase transformation we have. Let's come to the next topic, the concept of equilibrium. Okay, so here's two graph. You can see the rate versus time graph. As a system approaches equilibrium, both either it is forward or reverse reaction. At equilibrium, the forward and reverse are proceeding at the same rate. Guys, this is the graph for forward reaction. This rate is increasing, and after a certain time, this will become constant. And this is the graph for the reactant. Well, this is for product. This is for product because product is increasing. Earlier the product is 0, so it is increasing, and last it will become constant. This is for product. Product will be at. This is for reactant actually. So reactant will be at maximum value at t is equal to 0. As the time is increases, it will become smaller, and at last it will become at equilibrium phase. Let's see the next topic now. This next topic is a system at equilibrium. Once equilibrium is achieved, the amount of each reactant and product remains constant. Here NO2 and N2O4 has reached equilibrium. As you can see in the graph, here NO2 and N2O4 reach the equilibrium. Well, next topic is depicting the equilibrium. In a system at equilibrium, both the forward and reverse reactions are being carried out. As a result, we write it equation with the double arrow. Let's see, N2O4 is there, which is in gaseous phase, so which is reactant here, so it will form NO2. Here is the partial pressure of the above gases are equal. Let's see with the help of this figure. The first graph here, it is showing the N2O4, which is a reactant. As the time increases, the product is start forming here, and the color is start changing here. As also time increases, the number of product forming is increasing, and at last maximum number of product you will find. Equilibrium involving dissolution of solid and gases in liquid. Let's see the solid and liquids. When no more solute can be dissolved in the solution, it is called the saturated solution. Let's see better idea with the help of this example. Sugar is a solution. Now sugar is in solid, and also the rate of dissolution of sugar, that is equal to rate of crystallization of sugar. The ratio of radioactive molecules to the non-radioactive molecules in the solution increases till attain a constant value. Okay, so well, let's see the next slide. Gases in liquid and Henry's law. There is a certain equilibrium between the molecules of the gaseous state and the molecules of the liquid state. Carbon dioxide gas is there and carbon dioxide in solution. Henry's law states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. The amount decreases with increase in temperature. Let's see. First, solid to liquid in equilibrium. There is only one temperature, which is called melting point, at 1 atmospheric pressure, at which the two phases are coexist. If there is no exchange of heat with the surrounding, the mass of the two phases remains constant. Next, see the next one. Liquid to vapor equilibrium. The vapor pressure is constant at a given temperature. For dissolution of solid in liquid, the solubility is constant at a given temperature. Fourth one, for dissolution of gas in liquid, the concentration of a gas in liquid is proportional to the pressure of the gas over the liquid. Let's see the general characteristic of equilibrium involving physical process. Equilibrium is the only force possible only in a closed system at a given temperature. Both the opposing processes occur at the same rate and there is a dynamic but a stable condition. When equilibrium is attained for a physical process, it is characterized by a constant value of one of its parameter at a given temperature. The magnitude of such quantities at any stable stage indicates the extent to which the physical process has proceeded before reaching the equilibrium. Let's talk about the dynamic equilibrium. General case of an equilibrium reaction. If A plus B will give C plus D, with the passage of time, there is accumulation of the product C and D and depletion of the reactant A and B. This lead to a decrease in rate of forward reaction and an increase in the rate of the reaction. Finally, two reactions occur at the same rate and the system reaches the state of equilibrium. Let's see the law of chemical equilibrium constant. We know that the reversible reaction, which is A plus B, will give us C plus D. These reactant and products are balanced and hence we can relate them by equilibrium equation, that is Kc is equal to concentration of C product, that is C into concentration of D upon concentration of reactant, which is A and B, where Kc is called equilibrium constant and the expression on the right side is called equilibrium constant. At a given temperature, the product of a concentration of the reaction product raised to the respective stoichiometric coefficient in the balanced chemical equation. Well, the stoichiometric coefficient is nothing but here is the A, B, whatever, like 1, 2, 3 will get multiplied, right? The coefficient in the balanced chemical equation divide by the product of the concentration of reactant raised to their individual coefficients as a constant value. This is known as law of chemical equilibrium. Let's see, the equilibrium constant of a general reaction can be written as A, small a into capital A plus small b into capital B will give us small c into capital C plus small d into capital D. Here small a, small b, small c and small d is nothing but the coefficient. In general it is 1, 2, 3, maybe half sometime represented by, and capital ABCDs are nothing but the concentration. So what does the value of K mean? So the reactant will give product. If K is greater than 1, reaction is product favored, product is predominates at equilibrium. If the reverse takes place, then the former predominate. Well, if K is quite larger than 1, the reaction is product favored, product predominant at equilibrium. But if K is smaller than 1, the reaction is reactant favored, reactant is predominant at equilibrium. The range of equilibrium constants are small k, intermediate, or maybe larger. Let's see the homogeneous equilibrium. In an homogeneous system, the reactant and the product are in the same phase, like solution phase. And also we can say in the next reaction that the ions are equal. Here you can say all will have the in the same phase, gases, 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 right? Aqueous, aqueous, solid. If it is solid, then solid, solid. Okay. Equilibrium constant in gaseous system. We know that PV is equal to nRT. So P is equal to N by V RT. This N by V is nothing but the concentration. So we'll write P as a CRT. R is having the fixed value, which is constant 0.0831 or 821 bar liter per mole Kelvin. Equilibrium in a system having more than one phase is called heterogeneous system. For example, the equilibrium between water vapor and liquid water in a closed container in example of homogeneous equilibrium. Let's see the application. Application of equilibrium constant. Expression of equilibrium constant is applicable only when concentration of the reactant and the product have attained constant value at equilibrium state. The value of equilibrium constant is independent of initial concentration of the reactant and product. Equilibrium constant is temperature dependent, having one unique value for a particular reaction, is represented by a balanced equation at a given temperature. The equilibrium constant for reverse reaction is equal to the inverse of the equilibrium constant for the forward reactions. Let's see the predicting the extent of the reaction. The magnitude of the equilibrium constant Kc and Kp is directly proportional to the concentration of the product and inversely proportional to the concentration of the reactant. If Kc is very larger, then the reaction proceeds nearly to completion. If K is very small, then the reaction proceeds rarely. You can see with the help of this graph, reaction proceeds hardly at all if it is less than 10 to the power minus 3, and if it is greater than 10 to the power 3, reaction proceeds to completion. Predicting the direction of reaction. The equilibrium constant helps in predicting the direction in which a given reaction will proceed at any stage. For this purpose, we calculate the reaction quotient. Let's see, represented by capital Q, and it is generated by Qc with molar concentration. If Qc is greater than Kc, then the reaction will proceed in the direction of reactant, which is reverse direction. If Kc is greater than Qc, the reaction will proceed in the direction of product, that is forward direction. If both are equal, then the mixture has attained the equilibrium. Let's see with the help of graph. Here Qc and Kc is greater. Kc is greater than the Qc in the first graph. In the second graph, Qc is equal to Kc, while in the third graph, Qc is greater than Kc. So you can see the movement towards the equilibrium. Okay. So if Qc is greater than Kc, net reaction goes from left to right, and if Kc is greater than Qc, then the net reaction will go from right to left. And if it is both are equal, the no net reaction occur. Well, calculating equilibrium concentration. First of all, write the balanced chemical equation of the reaction. Under the equation, make the IC table. Then initial concentration, the change in concentration on going to equilibrium concentration, substitute the equilibrium concentration into the equilibrium equation and solve for x. If you solve a quadratic equation, choose the mathematical solution and make chemical sense. Calculate the equilibrium concentration from the calculated value of x. Check the result. and substitute them into the equilibrium equation. Next slide is relation between equilibrium constant, reaction constant, and Gibbs energy. Guys, we'll cover this slide in the next video. Thank you for watching. For watching next video, please subscribe our channel. Thank you for watching.